Okay, we need to do the chapter 7.1, exponential growth and decay, some exponential functions here. We will start with your packet, and we'll get right to it. First of all, types of graphs that we've seen so far. We've seen the parabola. This came up in, I think it was chapter 4, y equals x squared. Parabola, right? Parabola. And we have our vertex, and we had vertex form of a parabola, and it's y equals a times x minus h squared plus k, yada, yada, yada. And then we had a linear, y equals x plus 6. We did that in chapter 2. Chapter 2, linear function, y equals mx plus b, y-intercept, slope of 2, etc. And then we have exponential, y equals 2 to the x. Y equals 2 to the x. When we have a variable exponent, we have a exponential function. Variable exponent. The x is the variable. Exponential function is a function of the form y equals a times b to the x, where a is not equal to 0. That should be not equal. If you can't see that, that's not equal and not equal. B has to be greater than 0. B will always be positive. B will always be positive. Y equals 2 times 3 to the x. Notice, order of operations. You need to do 3 to the x before you multiply by 2. So the value of a here is 3. The value of b here is, the value of a is 2. The value of b is 3. Over here, this could be considered y equals 1 times 4 to the x. So the value of a is 1 and b is 4. B is the base. B is the base. A is going to determine the steepness of the graph. It's kind of like slope. It's also going to determine the initial value. A will always be the initial value. That's going to be where you're going to start. It's going to be kind of very similar to the y-intercept when we're not adding or subtracting. So y equals 2 to the x. If you think about 2 to the x, y equals 1 times 2 to the x. And if you just pull points, if x is 0, 1 times 2 to the 0. 2 to the 0 is 1, so there's my point 0, 1. Put in a 2. 2x is 2. Y equals 2 squared. That's going to be 4. So there's our ordered pair. So what happens over here? We have our y equals, when we put in negative 1, y equals 2 to the negative 1. That's y equals 1/2. So what's happening here? We're heading down, and then negative 2. 2 to the negative 2, that's 1 over 2 squared, that's 1/4. So we're going to have an asymptote at y equals 0, and then we go up exponentially, looks like exponential growth. But we'll never cross over into that negative line. Oops. Y equals 3 to the x, find the y-intercept, the asymptote, and state the domain and the range. So if you've got y equals 3 to the x, y-intercept will have to be, that's going to be when x is 0, that's the initial value. So the initial value is 1. Y equals 1 times 3 to the 0. 3 to the 0 is 1. Y equals 1. So my y-intercept is at 0, 1. Asymptote, we haven't moved up or down, so we're going to have an asymptote. We're going to be asymptote at y equals 0. The domain is always going to be negative infinity to infinity. And the range will bottom out at below my asymptote with 0. We can't be 0. We approach an asymptote, but we never are the asymptote. So then if we do 3 squared, we get 9er. So or 3 to the 1 is 3 first. 1, 2, 3. And then 3 squared is 9er. So this is going to go up very quickly. So here we approach on the asymptote. We come through our y-intercept, and we go up real quickly. If you think about 3 to the 1 is 3, 3 to the 2 is 9, 3 to the 3 is 27. And then coming back this direction, when we start putting negatives in, we get 3 to the negative 1 is going to be a third, 3 to the negative 2 is a ninth, 3 to the negative 3 is 1/27. So this is actually going to be real close to our asymptote. So the y-intercept is basically always going to be our value of a, and then we've got our asymptote is going to be, if we don't have anything, if we haven't moved up or down, which we will later in the chapter, it's basically going to be y equals 0. Domain is always going to be all real numbers, and the range is going to be wherever it bottoms out. Y equals 2 times 3 to the x. So now we've got the value of a is going to be 2, and then the b is 3, and then to the x. So my initial value, again, my initial value will be 0, 2. If you don't know that for sure, plug it in. Y equals 2 times 3 to the 0. Y equals 2 times anything to the power of 0 is 1, so I get 2. I get 0, 2. Y-intercept 0, 2. Asymptote, again, we are going to do my y-axis, x-axis, which is going to be y equals 0. Domain, negative infinity to infinity. Going to see that a lot. I can put anything in there for x and raise it to a power. And then the range, how low do we go? We bottom out at the asymptote. We never get to the asymptote. And then we sketch. And we're going to go up real quick, real quick. And that's what we're doing. This is the ball game here. Find the 1/3. How does this affect it? 1/3 to the x. 1/3 to the x. Let's see what happens when we put some values in here. So let's put in an x and a corresponding y, and we put in, let's put in like maybe -2, -1, 0, 2. So when we put these guys in, -2, 1/3 to the -2, actually that gets flipped over to 3 squared. Check it on your calculator if you don't trust me. I get a 9er. 1/3 to the -1 is 3 to the 1. It's 3. 1/3 to the 0, anything to the 0 is 1. Hey, there's my y-intercept. Not surprising. 1/3 to the 1 is a third. 1/3 to the 2 is a ninth. So look at what this looks like on an xy coordinate system. I got -2, 9er. It's going to be way up here. I got -1, 3. I got 0, 1. I got 1 1/3 and 2 1/3. So you can see this is going to be a decay instead of a growth. And we're going to still have a y-intercept of 0, 1, a domain of -infinity to infinity, a range of 0 to infinity. It's just going the opposite direction, but I'm still bottoming out down there. And I have a tote, an asymptote, totes my goats, of y equals 0, also known as the x-axis. So the difference between this one is my value of b is less than 1. Notice there is a value of a. It's standing there. There's a 1, and that's where our initial value is 0, 1. Okay, next we're going to move these things. I talked about moving them, and that's just going to change a couple of things just slightly. So if you think about, this is still 1/3, same base. H and K move things left and right. So if you remember back to y equals a times x minus h squared plus k, where the vertex was at h and k, this is going to go, h is going to go left and right, k is going to go up and down. It's going to do the same thing here. And how I like to do these guys are just like this. I like to take my 1/3, which I had on my previous slide, and I'm going to move the whole thing 2 to the right, and I'm going to move the whole thing 3 up. So if you think about the asymptote is going up 3, right? Up 3. So I'm going to go here with my tote. And all those points that I had on the last one are going to go from here, and they're going to go up 2. This is, or excuse me, right 2, and this was up 3. So when I think about my initial value, which was at 0, 1, instead I need to be thinking about that as that 0, 1 goes up from here, goes up to there, and then I'm 2 to the right. And that negative 1, 3, which was negative 1, 3, now it's got to go, up 3 from here, and then 2 to the right. So we're going to end up moving that whole thing over to here. So if you look at your previous graph of the 1/3 x, we move everything 2 right and 3 up. So you may want to think about graphing the original one and then moving it k units up or down, and then h units left or right. But just like my parabola, we got to remember that it's h units to the right. Okay, let's try this one. First of all, if I graph, let's just graph y equals 2 times 4 to the x. That would have a tote here, and we would be in an initial value of 2 because the a is 2, and then we would be going up like this quickly, right? But now I want to move the whole thing 5 units down, and there's my new asymptote, and I'm going to move this 2 to the left. So I'm moving this guy that was at 0, 2, it's 2 above the tote. I'm going to go 1, 2 to the left with that guy. Okay, and everything else is going to follow the same pattern. So I kind of think about moving this 5 down, and then I think about how this is associated with the asymptote. So this guy is going to come like so, and then it's going to go zoom. Okay, I'd like you to check that on your graphing calculator. I'd like you to plug in just the normal one. Then I'd like you to plug in this guy and see what's different. Okay, so if we had to name everything here, my asymptote is at y equals -5, and then my domain is at -infinity to infinity, and my range is at -5 to infinity because it doesn't change. Okay, so the whole thing just moved. We're looking at moving that asymptote, moving that initial value, and then we get the general shape. These are just sketches now. Okay, exponential growth and exponential decay, they've got a few different things here. They've got growth and decay on 2 separate slides. I prefer to combine them all together into one slide. So I'm going to do growth and decay. And what we're going to look at is y equals a times 1 plus r to the t. But r could be positive, means growth. That's when b is greater than 1. But when it's negative, it would be decay. And that's when our value of b is less than 1, greater than 0. Okay? So we want to think about growth and decay as exactly the same as y equals a times b to the x. And we have y equals a times 1 plus r to the t. So notice my a's are still my initial values. That's your initial amount. But your 1 plus r is replacing the b. So your r is your rate of change. So if we are growing at 5%, then my 1 plus r is 1 plus 5%. If we are decaying at 5%, then my 1 plus r is 1 minus 0.05 or 0.95%. Y is what we're looking for. T is time. It replaces the x. Let's take a look at a couple of problems. KCLD is having a radio contest. The contest begins with $100. Once a day, a name is announced. The person has 15 minutes to call in, or the prize increases by 2.5% for the next day. Write an equation to represent the amount of the gift cards in dollars after T days with no winters. Y will be the amount. Actually, usually we do amount after time T is equal to initial amount times 1 plus, we're increasing, whoops, that should be 0.025 to the T. So we can make this amount after time T is equal to 100 times 1.025 T. After 10 days, amount after 10 days, 100 times 1.025 to the 10th. Plug it into your calculator. If you called in and got it right on the 10th day, your answer will be $128. Plug it in. We already talked about decay. I prefer to use the other one. Use them together. So if we want to do decay, it says we are losing 6.6%. Original had 4,500. Amount after time T is equal to, started with 4,500 times 1 minus 0.066 to the T. In a single equation, we can do that subtraction. 4,500 times 0.934 to the T. After 7 days, amount after 7 days, 4,500 times 0.934 to the 7th. Grab your calculator, do some calculations. I get 2,790 cubic inches after 7 days. Got a slow leak. Got to plug it up. Get out the patch kit. They don't work. All right. Value of a new plasma television depreciates by 7% per year. Page purchases a 50-inch TV for $3,000. What's its value after 4 years? Round your answer to the nearest 100. Okay. I'm going to have the amount after T years is equal to original value times 1 minus 0.07 to the T. Amount after T years is equal to 3,000 times 0.93 to the T. Amount after 4 years is 3,000 times 0.93 to the 4th. And we get $2,244. If we round it, it's 2,200 buccarinos after 4 years. Who's paying that much money for a plasma TV anymore? No one. No one is. And we are done.